So what I'm going to look at today, we had a look yesterday, I think. Time just goes weird during term time. We had a look yesterday at, do you know what, I can't even remember. But over the last two lectures, we've looked at fitting models. We've looked at how important it is to look at things like error. We've looked at how models are defined by parameters, and that those parameters have confidence intervals and standard errors and stuff like that. So today is kind of moving on from that to have a look at when you actually get some data, what you should do with it before you start fitting those models. So it's looking for potential sources of bias, looking for things that are going to kind of mess up your model or give you a model that is a bad fit of the data. So we're going to look at some sources of bias, including linearity, outliers, normality, and homogeneity of variance, which is also sometimes called homoskedasticity, which is an arse to say at 9 o'clock in the morning. We'll have a look, I mean, you'll do this more in your practical, obviously, is how to use SPSS to look for these kinds of biases. And we'll also have a look at implementing corrections if you find that you have problematic data, which you probably will. So I just realised when I was looking at my notes that this slide is completely pointless because it says exactly the same as the previous one. So I'm going to go through in order outliers, just describing what they are. We'll have a look at an assumption known as linearity and additivity, which is not as it will take me like 2 minutes to explain. It's not nearly as complicated as it sounds. We'll have a look at the assumption of normally distributed something or other. And we'll also have a look at the assumption of homogeneity of variance, or as I said, it's often referred to as homoskedasticity in the context of regression, but it's basically, it's the same assumption whether you're testing groups or looking at a regression type of thing. So, as an example of outliers and what outliers are, now when I wrote the first edition of my textbook, it was a long time ago, and I was very, very excited, as you might imagine, because my parents basically don't think I've ever left school. So they have this kind of, it's like, what are you doing today? I'm going to work. And they sort of look at you as if to say, you don't have a job, you're still at uni. What do you actually do? So, and you say, well, I teach people and I do research. And they go, you're just at school. But when you produce a textbook, that's something tangible. They can show that to their neighbours and put it on a bookshelf and go, oh, my son's an author, and get very excited about it. So I was very excited because it was tangible evidence that I did something other than just turning up at uni and going to the pub. And of course, the other thing that you get quite excited about, having spent I think it was about 2 years it took me to write the first one, and it's like having a baby. Well, I haven't actually had a baby, so I don't know whether it's like having a baby, but I imagine it is. There's a long gestation period, and kind of the final struggle to get it finished and push it out is like incredible pain that you just can't possibly imagine. And then it's out there, and once it's out there, you feel like showing it to everyone and going, look what I've produced. Look what I've shat out of my body. It's a book. Isn't it impressive? And you want people to love it, to validate your existence. So, at least I did. Of course, what I did was I checked the Amazon ratings, like really religiously, to see if anyone had rated it. And the first person who rated it was, in fact, a bastard, or a not very nice person. So they gave it a rating of 2. There. Now I thought, what a git. I spent 2 years writing this, and I put quite a lot of work into it. I had a lot of sleep deprivation during that time, and okay, it's not perfect, nothing's perfect, but I tried really, really hard, and then this person just sitting at their computer, like in a bit of downtime when their porn's seized up or something, decides, I'll just knock up a review on Amazon of this book, and gives it a 2. What a bastard. So, obviously, I emailed all my friends and said, can you go and rate it a bit higher, because it's looking a bit bad at the moment. I've got no idea why my mum only gave it a 4, but anyway. Anyway, my point is, when you looked at these are, there's more ratings on there now, because, I've emailed everyone in the world. But at the time that I was slightly more obsessed than I am now about these things, these were the ratings that I had. So this was like back in about 2002 or something like that. And you can see that most of the ratings are pretty respectable. There's some 5s up the top here. There's Mum, as I like to call her, with a rating of 4. Now what happens is if you ignore the nasty, horrible, evil person, then basically I got a fairly respectable mean, this blue line here, of nearly 5. And in fact, these days, Amazon will round that up to 5, so happy days all round. But if you include the outlier, if you include this score of 2, what that does is it drags down the mean. So outliers are sources of bias. Now, all they are scores that are sort of substantially different from the rest. And in this case, it's only a small number of scores, but that person's rating is sort of out of kilter with everyone else's. So this is a very simple example of what an outlier is. It's just a score that's very different from the rest, and it has a bias in effect. In this case, it drags the mean down. The mean would have got rounded off to about 4.5. So, in practical terms, that might have had some kind of impact on people's perception of the book. Now, subsequent to this, I've got a bit of an obsessive personality, I think. I got so obsessed with this person and stuff that I ended up tracking them down. Spent loads of money on a private investigator. And I tracked them down to a small farm in Scotland. And I can now reveal to you a photo of what they look like. So that when you see them, you know this is a nasty, evil person. There they are. So, that's what an outlier is. So what about this assumption of linearity? Now, I mentioned, in fact, I keep mentioning it. In fact, you're probably bored of me mentioning it. That there's only one equation that you ever really need to understand, which is we predict outcomes from some kind of model, and there'll always be error associated with those predictions. And I've also mentioned a number of times that the model we tend to fit is a linear model. So this thing in the brackets here. And it has some parameters that define it. Those B's are values that tell us something about the relationship between the predictor variable and the outcome. So this is our model. Now, all the assumption of linearity is that the model we're fitting does actually represent reality. So we fit a linear model. We fit a model that basically represents a straight line, or it can get more complicated, and then it's not really a straight line, but it's a linear something more complicated than a line. So the assumption of linearity just means the relationships that we're trying to model should actually be linear, because if they're not, then we're fitting a model that just doesn't really represent reality at all. So we'll come back to this a little bit in 2 lectures' time, but I just wanted to flag it here as something important. So when you look at your data, you're really trying to get some kind of idea of whether, in reality, there is a sort of a linear pattern in there. Because if there's not, then basically all the statistics we teach you as psychology undergraduates don't really make much sense as models of those data. Now, there are things you can do, but they get quite complicated. So as far as you're concerned, everything you learn about is a linear model. So the relationships you're trying to model have to be linear in the first place. Otherwise, it's obviously self-evidently not going to be a good fit. So in terms of assumptions, the 2 big things that people tend to remember in psychology are there's an assumption, something to do with normality. They may not remember exactly what it is, but they know that normality is important. And the other one is this homogeneity of variance thing. So we'll have a look at those. The normally distributed something or other. Why have I said something or other? Why have I not said normally distributed data? That's because it's a misunderstood assumption, typically. So normally, and this would, I reckon if you took a bit of a sort of a straw poll around the faculty in our department as well, you'd probably find quite a few of them saying that it was the data that needs to be normally distributed. That's what people tend to think. Your data have to be normally distributed for the models that we fit to work. Now, actually, that's not strictly speaking true. It's not the actual data that matter, but we tend to use the data to work out whether the things that matter are actually normally distributed or not. So what actually matters is if you're doing significance tests or constructing confidence intervals, which we talked a bit about yesterday, then what has to be normally distributed is the sampling distribution, not the data themselves, the sampling distribution of whatever parameter it is you're significance testing. So if you're computing a mean, which is a parameter, and you want to significance test that mean, or you want to construct a confidence interval around that mean, then the sampling distribution of that mean has to be normal, basically. If you're doing regression, then the sampling distribution of the regression coefficients needs to be normal for those significance tests and confidence intervals to be accurate. If you're not worried about significance tests or confidence intervals, then normality doesn't matter. The other area in which normality matters is the estimates themselves, so the betas in the model, the method of least squares is optimal, so it gives you the best results if the errors in the model are normal. So there's two things that potentially need to be normal. One, the sampling distribution of the parameter. So if you're looking at means, the sampling distribution of the means. And the other thing is, once you've fitted your model and worked out the errors or the deviations within the model, those deviations should be normally distributed too. And if they are, that means that the estimate you've got is optimal using the method of estimation that we use. So, just to remind you of what a normal distribution looks like, this is what it looks like. It has a very characteristic shape. So, you may have seen one of these before, whether you've done research skills or not. So, basically, you've got scores ranging from low to high along the bottom, and then you've got the frequency with which the scores occur along the y-axis. So you get a very characteristic shape where small scores don't happen very often. So the bars are quite low at the low extreme. So it's, I mean, if you imagined like this was, you know, I don't know, age at which you die, or something. That's a bit of a depressing example, but it's sprung to mind. The age at which you die, not very many people die very, very young. So you'd get only a small cluster of people there, thankfully. And you also don't get too many people dying very, very old, because, you know, most people sort of don't live to 112 or whatever. So what you get is a big cluster of people in the middle of the distribution, like that. So it's got a very characteristic shape. And of course, if you look at something like the mean, then that divides the distribution exactly into two. So it's a symmetrical distribution, and it has a very characteristic shape. Not many scores at the high end, not many scores at the low end, and a big cluster in the middle. So you get this characteristic bell-end-shaped curve. So that's what a normal distribution looks like. So you recognise one when you see one. The other thing worth pointing out is if you've got grouped data, so imagine you were comparing two different groups of entities, what matters is not the normality of the whole kind of sample or whatever, or the whole, or the sampling distribution of the whole group. What matters is the distribution within each group. So here, for example, if you imagine we took a measure of happiness, that will cheer things up from the slightly odd death example that I just popped out of my head. So we measured happiness. And let's imagine the film The Muppets was out last year. And when I was a kid, I loved The Muppets. So we went and saw it. We were the only adults in the cinema who did not have a child with us. But nevertheless, it was a good film. Well, if you like Muppets. Muppets are typically happy things. So if you were to sort of test a sort of a random sample of the world, and within the world there are humans, there are some Muppets floating around, probably. If you measured happiness, you would get probably quite distinct distributions. Muppets, I reckon, on balance, are typically happier than humans, apart from Oscar the Grouch. He's a bit of a mizzo. But most of them, I mean, Kermit, he's insanely happy. Pathological, I would say. So you've got two distinct groups there. So if you split them apart, if you actually said, well, let's do the distribution for Muppets and let's do the distribution for humans, you would get something like what we have on this side of the screen. So you get these sort of, actually I've got a pointer. You get these two sort of, they're a bit stretched up because of the way I've done the graph, but they're basically two normal distributions. And that's what you want, that's fine. But if you combine these, so if you just mashed all those scores together and didn't worry about whether they were Muppets or humans, what you actually get is a distribution like, what distribution is that?
It's a mixed Gaussian.
That's too posh an answer. What characteristic does that have? Bimodal, fantastic. So that's a bimodal distribution. There's two humps, looks like a camel, sort of, without a head or any legs. So you get a humpy distribution. So if you looked at normality within the sample as a sort of a big whole entity, then what you'd see is something like that, and you'd panic and you think, oh my God, the world's going to end. But actually, that's not what matters. If you're looking at grouped data, if you're comparing groups, then what matters is the distribution separately within each group. Or that's where you end up looking at that as a way of assessing things. The other thing worth explaining is the central limit theorem, which I don't know whether you will have covered before. But this is quite important. And Basically, the central limit theorem, I don't really understand mathematically because I'm not that great at maths. But essentially, it's a principle that works in practice, but there's some complicated maths behind it as well. So if you imagine this is a population of scores, okay? So this is just like, maybe like 1 million scores or something like that. So this is the actual shape of the population. We don't normally have access to that, but with a computer, if you're randomly generating numbers, you can create yourself a nice big population. So this is a population. Is that normally distributed? No, not at all. I can't remember what distribution I used, but it certainly wasn't normal. So that's not normally distributed at all. It's very easy to see that it's not. Now imagine that we took a sample from that, so a little sample of maybe 10 scores or 5 scores or 30 scores, and we calculate a parameter. And let's say it's the mean, because the mean's easy to deal with. So we've taken a sample out of here, we've gone and nabbed sort of 5 scores, and then we compute the mean. And then we put those scores back. And then we take another 5 scores, and we compute the mean, and then we put them back. And then we take another 5 scores, compute the mean, put them back. And let's say we did that, say, 5,000 times. So we'd taken 5,000 samples, and in each sample we'd calculated the parameter we were interested in, the mean in this case. What you find is if the samples you take are small, so if you take samples of, say, 5, which is pretty small, the distribution of those parameters ends up looking slightly like the population. So it's very, very skewed. So most of the means here are at the low end, and you don't get very many high means. So you get and this is actually a sampling distribution. It's the distribution of parameter estimates from taking lots and lots and lots and lots of samples from the population. So if you have small samples, you get you get a distribution that sort of resembles the population. What about if we took bigger samples? Let's imagine we did the same process all over again. This time we took 30 scores, calculate the mean, put them back, 30 scores, calculate the mean, put them back, 30 scores, calculate the mean, put them back. And we do that 5,000 times again. With our bigger sample, the distribution of these parameters, the distribution of the means that we've calculated, is starting to get a bit more normal. What about if we did the same, we're getting bored now, surely, but let's imagine we did the same thing, but this time each sample has got 100 people in, 100 scores in. What happens? Our sampling distribution is now pretty normal. So, the central limit theorem, all it basically says is as your sample size gets bigger, the sampling distribution of your parameter, whether that's the mean or a regression coefficient or whatever, the sampling distribution will start to approximate a normal distribution. And this is just, basically an example to show that it kind of works, rather than trying to learn the maths so that I can fail to explain it to you properly. So the central limit theorem is important because if you remember a couple of slides ago, I said what actually matters is the sampling distribution, not the data themselves. So if we have large samples, and there's a whole debate about how large they need to be, but if we have large samples, then we can pretty much always assume that the sampling distribution will be normal because the maths behind the central limit theorem tells us that it will be. So if we're dealing with, if you've got massive sample sizes, if you come to do your third year project and you end up collecting, a couple of hundred participants or something, which some of you will do and some of you won't do, depends on the kind of research you're doing. If you're collecting large numbers, you can probably pretty much ignore the assumption of normality. So normally distributed something or other. Now, as I said, just to recap, what normality affects is significance tests and confidence intervals. And what matters there is the sampling distribution. And as we've just seen, that only really matters if you've got fairly small samples. And for the parameter estimates to be accurate, it's not the data that matters at all, it's actually the errors in the model. And we're going to cover that in a bit more detail in a couple of lectures, so I don't want to dwell on it here. But that's what it affects. So when does normality matter? Well, as I said, people tend to look at the data to assess normality because we don't have access to the sampling distribution. And therefore, if the data are normal, it's a reasonable assumption that the sampling distribution is normal too. So that's the only reason we look at the data. It's just because we don't have access to the thing that actually matters. So I said yesterday, sampling distributions are a bit like unicorns. They exist sort of hypothetically, but you'll never see one. The central limit theorem tells us that when we have big enough samples, the sampling distribution will be normal anyway, so we can probably stop having a panic about normality. So, That's all you need to know about what normality is. So what's the assumption of homogeneity of variance? Again, this is easier to explain if we think about it in terms of groups of data, although the same principle applies if you're doing if you're looking at relationships. So I periodically get worried about my hearing because I've spent way too much of my youth going to concerts in the days before people used to tell you to wear earplugs. And I'm also a drummer, which is not good for your hearing. And I used to be a guitarist, which is also not good for your hearing. So all round, my ears should be screwed. So here's an example of if we wanted to look at this. So we followed a band across their tour. So they start off at Brixton, Brighton, then Bristol, Edinburgh, Newcastle, Cardiff, and Dublin. And we've those flaggy things don't appear as flags on my Mac, but anyway, those flaggy things are just representing kind of the mean score of the group. So we've got what we're expecting is a sort of cumulative effect as people go to more and more concerts. The ringing, the number of hours that their ears are ringing for, goes up because they're getting sort of progressive damage. Now, what we can look at is the sort of variance of their scores. So these data points here represent different people, and they seem to appear as peace symbols, which is kind of cute in a way, but not what I intended. So you've got you've got a variability in scores essentially, so people are sort of clustered around the mean. Now over here we've got, say, a different study, a different group of people who also followed the band on concert, on their tour, so they went to lots and lots of different concerts. Again, we've got progressive increment in the number of hours that their ears are ringing for after each concert. But what we're interested in, again, is this spread of scores around the mean, and you can see that they're a lot more spread out than the original group. So let's actually look at the spread. This is very crude. We're not really looking at variance here, but it will give you the gist of the idea. We're just looking at the sort of the spread of scores around the parameter that we're interested in, which is the mean in this case. And you can see in this first group of people, these bars are pretty equally long. So the variability is quite similar at the different concerts. So this is an example of homogeneity of variance, the spread of scores at the different points on the tour, if you like. So as we sort of go through the tour, the variability in scores is remaining relatively constant. When the assumption's broken, that's known as heterogeneity. And we can see this scenario over here. So we start off with relatively compact group of scores, but as the tour goes on, the scores start getting more and more spread out, more and more variable. Now if we get rid of the graphs, just to really ram this point home, you can see that the amount of spread we got on this side, all those bars, all that spread's relatively similar. So the variances are homogeneous, whereas over this side, they're quite different. So the spread here is much, 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 much less than, say, over here, and loads less than over there. So that's all homogeneity of variance is. It's kind of saying as your predictor variable, whether that's a grouping variable or not, as your predictor variable changes at each level of it, you should have a similar spread in your scores. So, how do we unearth bias? So how do we look for this kind of stuff? Well, first of all, if we want to look for outliers, simple graphical techniques like boxplots and histograms, we'll have a look at some of these in a minute. The other thing you can use is use something called a standardized residual. Now, I mentioned yesterday that in statistics, things often get called by different names. So residual is just an error or a deviation. And what you can do sometimes is to get SPSS to chuck out the residuals or the errors for each data point. So it will just tell you the deviation, if you like, between each data point and what the model predicts. And that model may be a mean, for example, or it may be a regression model or whatever. And what you can do is standardize it. And the purpose of standardizing it is, all that means is you convert it into a z-score. And all that means is that regardless of your units of measurement, it doesn't matter what you're measuring, you can have sort of cutoffs that apply across the board. So standardized residual, it's just the error for a particular participant expressed as a z-score. So expressed basically expressed in standard deviation units. Now, if your standardized residual is greater than about 3, then that's possibly an outlier. If it's greater than 4, that's almost certainly an outlier. So you can look at standardized residuals, but you can also do sort of more general things than looking at individuals, like just say, you know, how many standardized residuals in my sample are big, and if a lot of them are big, then it probably means that, you know, your model's not a good fit. In terms of normality, again, box plots and histograms can be quite useful for looking at normality, and also things known as PP and QQ plots. Now, PP and QQ plots basically show the same thing, but in slightly different ways. But you interpret them in exactly the same way. So I'll talk about one of them, but everything I say about, you know, a PP plot applies to a QQ plot as well. So don't worry too much. You can quantify various characteristics of a distribution. So you can look at the numerical values of skew and kurtosis, for example. So skew is just how symmetrical the distribution is, and kurtosis is to do with how many scores there are at the extremes, essentially. So often people talk about kurtosis in terms of whether the distribution is flat or pointy. It's not really about that. It's to do with how many, whether you've got more or less extreme scores than you're expecting. But one of the knock-on effects is that can make the distribution flat or pointy, but that's not really what kurtosis actually is. It's to do with how many scores you've got at the extremes. As far as SPSS is concerned, it gives you values of 0 for a normal distribution. So values of skew and kurtosis that deviate from 0 are potentially signs that you have some skew or kurtosis. Now, obviously, you'll never actually get a skew value of 0 out of any data that you collect in the real world. So it's really it's a judgment call about how far from 0 it is, and I can't really give you any particularly helpful guidelines on that front. But certainly, if you're getting like really, really big values, then you know something's wrong. But essentially, it's weighing up evidence, really. You look at histogram, you look at the value of skew. If the histogram looks pretty normal, personally, I probably wouldn't bother too much with the skew value. The other thing you can do is you can do some formal significance tests, and there's a test of normality known as the Kolmogorov-Smirnov test. And it just simply tests whether your data are significantly different from normal. So if it's significant, if the p-value is less than 0.05, then your distribution is not normal. And if your significance value is above 0.05, your distribution is normal. So let's have a look at some of these in practice. So here's a real research example. This is a study that was done in, I can't remember, 2000 something or other. And what they were looking at is, it was by Pedersen and colleagues, and they were looking at evolved sex differences in the number of desired sexual partners. Now, what they did is they took a group of college students, and they asked them various questions, but one of those questions was, how many sexual partners would you like to have in the next 20 years? And I actually, I have the data from, I haven't made this up, I have the actual real, genuine data from the study. So, let's have a look at what happened. Well, if you split the data by gender, you find that males, on average, report that they would like to have basically 65 sexual partners in the next 20 years. And females are a more respectable 2.81, so around sort of 2 or 3. Now, one big, I'm going to come back to homogeneity of variance, but one big clue as to whether you've got unequal variances might be to just look at the variances. And in this case, the variance in the male sample is 342,000, pretty big, compared to only 19 in the females. I think that's a pretty clear-cut case of heterogeneity of variance. But anyway, I'm getting ahead of myself there. So let's have a look at the actual distributions. Well, here's the distributions. The males are over here, the females are over there. Now, the female distribution is actually relatively skewed. The pen thing's not working, so I'm going to have to rely on my artistic skill with a mouse. Oh, not too bad. So you've got a skewed distribution there. So there are some kind of extreme scores. So there's someone who's reported they want 30 partners in the next 20 years. But basically, so there's some bias in there. There's definitely some kind of outliers, and that's skewing the distribution because most people are sort of clustering between 0 and 10. The male distribution looks very, very odd indeed because there's just like a big spike, and then this chappie over here. And the reason I use these data is this is a very good example of a very obvious outlier, because it turns out that if you ask about 106 men how many sexual partners they would like in the next 20 years, you're going to find one arse who sits there and says, well, I don't want to have just one. You know, variety is the spice of life, but I need to think carefully about how many. 6,000! That should do the job. I think I can die happy if I've had 6,000 sexual partners in the next 20 years. So he's an outlier. He's a strange case in more ways than one. So this would be an example of a very, very extreme score. But actually, because he's so extreme, he's made the histogram a bit difficult to interpret. Now, if you look at a box plot of these same data, this is quite useful in that, well, we can sort of identify extreme cases. And there's more than him. If we take him out of the mix, if we take Mr. 6000 out of the mix, there are still lots of other outliers that are quite extreme. And you even get some extreme scores in the females. These extreme scores have been compacted a bit by the fact that the extreme scores for the males are so much more extreme than the females. So it's kind of compressed the female data a bit. But essentially, box plots in SPSS will flag extreme cases to you. So if there's an asterisk, it's an extreme case. If there's a circle, it's an outlier, which is not as bad as an extreme case, but it's still something to look into. So box plots very, very handy for looking for outliers. And here's the QQ and P plots that I was talking about. Now, in an ideal world, basically what you'd see, so what this is plotting is the values that you would expect to get from a normal distribution against the values that you actually observed in your data. So in an ideal world, you get, in fact, the graph helpfully puts it there for you. You get a diagonal line. So your dots should fall almost exactly on that diagonal, and that would be a perfectly normal distribution. So that's an example of what normality looks like. And here's our male data. And you can see it's really very, very non-normal. So this diagonal, again, is what we're aiming for. But what we actually get is something more like that. That's just, I mean, this is such an extreme case that this is like a really, really bizarre PP plot. Sorry, it's a QQ plot. So it's, it doesn't go anywhere near the diagonal. Now, basically, if you get a sort of a snaking of dots around the line, then that represents skew. If you get a sort of consistent dip below the line, that represents kurtosis. But essentially, you're just looking for anything that doesn't fall on the line. Now, the female data are not quite so squiffy as the male, but even so, you're still getting, it's nowhere near the nice straight diagonal line. So these are both very, very clear examples of non-normal data. So graphs are very, very useful indeed. As I said, we can use numbers. So if we look at the values of skew and kurtosis for the men, as you might expect, they're way, way high. I've never, ever seen a value of kurtosis of 100 in my life, apart from in this data set. So these are really, really extreme scores. But really, like in the females, a skew of 4, I mean, we could see from the histogram, it was a very, very skewed data set. So this gives you some idea of, 4 would represent a reasonably obvious amount of skew. And again, the kurtosis is very, very, very high because we've got some, because the tails of our distributions are very weird because they're so skewed. So we can look for just extreme values there. And like I said, 4 is a reasonable sort of cutoff for worrying about things, but it does depend a bit. And we can also do the KS test. So what you get out of SPSS is just a significance test that tells you whether your data are significantly different from normal. In this case, as you might expect, very, very significant. P-value is 0, much less than 0.05. Therefore, we would conclude for both males and females that distribution is non-normal. However, I have a warning. If I can actually get this video to run. There's something really weird that goes on with this system when you... Oh, I don't want my drawings. Sorry. Right, so I have a warning from the cat of statistics.
Shall we test normality with a KS test?
I'm sorry, I'm really easily amused, especially when it comes to cats. So I just want to add a word of caution. Now, I mentioned yesterday that significance tests are dependent on your sample size. So if you have big samples, you can get significant results even from very, very small effects. And this is particularly relevant for things like the KS test because, for example, in this in these data, if we lump the males and females together, we have a sample of about 260, which is quite a big sample. So even if you had a reasonably normally distributed data set, you would quite likely get a significant KS test if you had a big sample. So I'm not saying don't use KS test, but I'm just saying evaluate a KS test within the context of how big your sample is. If your sample is small and you get a significant result, then trust it. If your sample is big and you get a significant result, you probably want to just kind of look at a histogram instead. And by big, I mean sort of 100 or more. Okay, what about homogeneity of variance? Again, we can look at box plots. We can look at error bars, especially if we plot standard deviations. They're useful. And again, I'm going to talk about this in lecture 6. We can look at the errors in the model and make some assessment based on those. We can look at the actual values of the variance, and some people look at something called the variance ratio, where you just divide the biggest variance by the smallest one. And there's a sort of general rule of thumb that if that's under 2, then everything's all right. But that's well, as far as rules of thumbs go, it's a bit sort of rigid. It actually depends on lots of things what your rule of thumb should be, like how many variances you're comparing for a start. But if you want a rule of thumb, that's a reasonable one to use. And again, there's a significance test known as Levene's test. It's the same principle really as a KS test. It's just testing whether the variances are significantly different. So if you get a significant result on Levene's test, then it means that your variances are unequal. In other words, the assumption's been broken. But if your Levene's test is non-significant, then it means your variances are approximately equal. So again, I would, when you're looking at data, you don't just use one of these. You would do lots of things, look at graphs, maybe do Levene's test, look at the actual variances themselves, and then pull that evidence together to make some kind of decision about whether you think you have a problem or not. So I'm going to use a different example now, and I like to spend my spare time discovering strange research that people do. So when I'm bored of doing my job, I kind of do something related to my job, which is go and look at research articles. And one endless source of bizarre research is a journal called Surgery. And one of my favourite articles that I've ever found in Surgery was this article about a traumatic rectal perforation by an eel. Now, basically, the story goes, and I'm going to embellish this a bit and make it sound like I was actually there when I wasn't, but basically a 50-year-old man went to A&E in, I think it was Hong Kong, reporting abdominal pain. So he turns up in A&E, oh, I've got abdominal pain, but in a bit more of a Hong Kong accent. And the doctor said, oh, okay, what seems to be the problem? Oh, I don't know, the pain. So, well, have you eaten anything strange recently? No, I'm just in pain. Has anyone punched you in the stomach? No, oh, the pain. Have you drunk anything weird that might have fermented in your stomach? No, but I'm in so much pain, help me. So, okay, so there's absolutely nothing you can think of that might be contributing to your abdominal pain. No. It's like, oh, well, okay, we're gonna have to x-ray you. So they rush him along, they put him into the x-ray machine, they x-ray him, and lo and behold, he comes out, the doctor looks and sees the shadow of an eel. And the doctor thinks, I wonder how that got there. Maybe there's an eel in the scanner. So then they went away, they did another x-ray on an old woman's head, no eel. So they knew it wasn't in the scanner. So then they came out to the guy and they said, well, look, we've done your x-ray and there appears to be an eel inside you. And that, maybe that's contributing to your abdominal pain. Is that likely? He went, oh, yeah, the eel. Oh, yeah. I didn't think it was that relevant when I came in, but I did pop an eel up my anus this morning. Do you think, doctor, that's what's causing the problem? Now, personally, I feel quite sorry for the eel because, I like animals, even eels. And I think, the eel is probably swimming around in the morning thinking, nice day, nice water. I'm an eel, I don't have a job, I don't have to worry about homogeneity of variance. What could possibly go wrong? And then, the 50-year-old hand comes in and it's like, oh, where am I? I'm in a dark tunnel. It feels claustrophobic. Doesn't smell too good either. And like any self-respecting eel, he tried backing out. Nothing going on there. It's it's one-way street. And so he decided to eat his way out. I know. Can't blame him though, really. So the abdominal pain was in fact caused by the eel trying to chew his way out of the man's stomach. There's a moral here for us all, I think. Yeah. Sadly, the eel didn't survive, which is the saddest bit of the story. The other thing about this story is that since I've put this example is in my textbook somewhere, and since I put it in, I get loads of eel mails from people. Like, literally, I bet you, whenever anyone in the world puts an eel up their anus, I'm one of the first people to know. I just get email so this literally, I mean, completely coincidentally, 3 days ago, someone emailed, I'm not going to stop saying that. Someone emailed me this story about a New Zealand man who gets an eel stuck up his butt. And someone topped it all last year by sending me a story about an eel removed from a man's bladder after entering his penis. Now, according to this story, it was like, those fish pedicure things. He was having like an all-body fish eel chewing of the flesh or whatever, and I guess one of the eels just thought, you know what, I'll just zip up his cock. And one of my students last year said, you know what, you really ought to have this in your lecture. Trouble is, I have that song permanently in my head. Eels up inside ya, finding an entrance where they can. Pouring through your mind, through your tummy, through your anus. Everywhere I go, anyway. So, the point I was getting to, believe it or not, was when the man was questioned about why he had put an eel up his anus, his response was to cure constipation. Now, I don't know about you, but I thought the definition of constipation was having a blockage in your anus. So I'm not entirely sure how blocking your anus helps with a blocking of your anus. But, I'm no medic. Anyway, so I thought, you could put this to the test, essentially. As a scientist, I shouldn't be judgmental. Maybe eels like to eat poo. Could work. So you could do a clinical trial. You could have a group, you wouldn't, but you could. You could have one group of people and they're given eels to cure their constipation, and you could have another group of people who are given treatment as usual or waiting list or something. And then you could test it out. And then once you were looking at your data, you'd want to know whether you had homogeneity of variance. So what you could do is, I'm going to come back to this again in the lecture on regression. But you can look at graphs. So when we look at errors in our model, which we're going to do in a couple of weeks' time, and I'll bring this up again, I just want to sort of flag it here. We're looking for this sort of thing. So the spread of errors should be pretty much the same across that graph. You get heteroskedasticity or a lack of homogeneity if you see a funneling shape like this. So the spread of errors is kind of quite low at one end and quite wide up the other end. And, it doesn't have to be this way round. The funnel could, be flipped the other way, but just some kind of funneling shape. Also, going back to the assumption of linearity, we can look in our errors for non-linear relationships. So this would be an example of where we'd violated the assumption of non-linearity. And if you're really unlucky and you violated the assumption of homoskedasticity and linearity, then you get this sort of peculiar, sort of bendy sausage funnel weird thing. Like I said, I'll come back to that when we talk about regression, but I just want to flag it here so that you hopefully remember that we're sort of talking about the same thing. Now, obviously, you can just look at variances, so look at them as numbers. So in our no treatment condition, we've got a variance of 2.6. In our eel condition, a variance of 9.38. They're pretty different. It's more than 3 times greater in the eel condition. If we plot standard deviations on as error bars. So these are not confidence intervals, they're standard deviations. You can see here that the standard deviation is much smaller in the no treatment than the ill condition. So graphs can be quite useful. And even box plots, if you look at the sort of the middle, so these boxes are the middle sort of 50% of scores, they can give us some idea of whether the scores are more spread out in one group than another. And again, you can see, I mean, generally the range of scores is much wider in the ill condition, but also the sort of central 50% of scores, the box, is a bit more dragged out as well. So you can use graphical techniques. As I said, you can also use Levene's test, which looks something like this. So just like the KS test, you basically are looking at the significance value. It's highly, highly significant, which is showing us, again, that there's a problem with homogeneity of variance. So you'll learn how to do this all in a practical class. Again, I have a caveat about Levene's test.
Levene's test.
Which is, as with any significance test, it depends on sample size. So if you've got really, really big samples, then take Levene's test with a pinch of salt. And don't sort of get too excited about it. I mean, the opposite is true also. If you've got really small samples and it's non-significant, then you might still have a problem. So again, as I said, it's accumulating evidence from different sources. So how do we correct problems? Well, essentially, there's a nice acronym called TWAT. Most of which we don't cover. So we can trim outliers, we can just get rid of them. We don't really talk about that because it's really, you can't really do it very easily on SPSS. You can substitute outliers with the highest value that isn't an outlier. Again, not very easy to do on SPSS. So what we concentrate on in this course are using something called bootstrapping and transforming the data. Now, I'm going to talk about bootstrapping a bit more when we deal with regression, because that's when you're first going to start using it. You don't actually use it in your practical. So I'm going to come back to bootstrapping and do that in the regression lecture. What we're interested in instead is transforming the data. So, sorry, I just want to skip ahead. So you can implement transformations. This is what you're going to be doing in your practical class to correct for things like skew. So, if you had a skewed distribution like that, and you log transform all your scores, it tends to bring the skew in from the edge a bit, so you get a slightly more normal distribution. So for these particular data, it hasn't corrected it perfectly, but the skew is kind of better than it was. And you can sometimes use a square root transformation as well, which the basic principle is kind of the same. So you're just square rooting every score. So if your score is 100, it becomes 10. And you can see, actually, for these data, that has quite a nice effect in making the distribution more normal than it was before. So your practical is going to show you about transformations, and then we'll come back to bootstrapping in the regression lecture. But I just, again, want to flag it here as something, it's a correction that you can apply to deal with these sorts of problems, just so that when we talk about it again, you'll remember. Sometimes you have to, if you do a transformation, you have to apply it to all the scores that you have. There are situations where you can, so in regression, for example, you can only transform one predictor, and that's fine. But in other situations, if you're looking at sort of differences over time, if you correct one variable for skew, you would have to correct them all. And I just, again, want to flag the fact that if you start off with a normal distribution and you, say, apply a log transformation, it will actually skew it a bit. So you can end up in situations where a transformation helps with one of your variables, but because you have to apply it to all your scores for the particular thing you're doing, it ends up creating a problem for a different variable. So it's not always a magical solution, but it's just something to bear in mind that is sometimes useful. So finally, I want to leave you with a song, because I like music, and this is to help you remember about the KS test, even though I said take it with a pinch of salt. And I have to tell you what tune it's to, because I'm not a very good singer. It's to the tune of Britney Spears' Hit Me Baby One More Time. And it goes. My distribution is killing me. Why can't it be shaped normally? Normally! My KS test is significant. It is a sign to transform my data one more time. I'll see you next week.